Hey guys, welcome back. Day 9. We're going to do some more integrated rate laws. Right, and this is what we just covered. We derived 3 rate laws from the zero order reaction, first order, second order. Right, we got the rate law, the units of K, integrated rate law, which we just derived. The straight line plot tells you the slope, which is always K or negative K, and the half-life expression. So let's summarize these real quick. All right. So if we talk about the summary of basic kinetic relationships, the reaction order, right? The reaction order, which is the exponent right here, all right, in the rate law. The reaction order and the rate law must be determined experimentally, right? So we can't just look at a reaction and say, oh, it's second order. It doesn't work that way, right? It's always determined through experiment. And the reason it's that way is we can't see the individual atoms or ions or molecules, particles interacting. We can't see how it's done. We physically can't see the electrons and where the electrons are moving. Right? We can, come up with very good theories on what's going on and very predictable behavior, but we can't actually observe them. All right? We can observe outcomes, we can't actually observe the process. So that's why it's a difficult situation. So this method of initial rates we actually can see how the rate's affected and come up with the reaction order based on an experiment, which is fabulous. All right, then we got the rate law from that experiment. It relates the rate of the concentration or the reaction to the concentration. So it relates rate, how fast the reaction is going to go, to how much reactant you have. Right, and whether it's first order, it doesn't matter how much reactant you have, or it matters as reactant A increases, the rate increases, or whether it's exponential, where if you double the rate of, or double the concentration of A, you double the rate. Okay, and so now we have the rate law, and you have the relative rate. And the relative rate is just whatever the speedometer is of the reaction at that time. It's reacting at 2 molarity per second, or 4 molarity per second, 0.01 molarity per second, whatever the rate is, how much we're using, right? Like if you're talking about Dunkin' Donuts, there's a Dunkin' Donuts across the street from the college that in the morning it is packed. Like sometimes the line to the drive-through, which is quite long, sometimes that's on the road, right? Where people are stopped on the road trying to turn into this place, right? And they have a rate of how many donuts are served per hour. Right, it's just a rate. It's 500 donuts an hour, 250 donuts an hour. I don't know what the rate is. How many coffees they serve or whatnot. They have rates for this stuff. Okay, so it's a rate, just how much reactants you use in this reaction. Then we have the integrated rate law, which again, using calculus, we just do some math and we get the rate from the rate law, and that relates concentration to time. Right, so we know after 15 minutes, so go back to Dunkin' Donuts, right? If they're doing 100 donuts an hour, we know after 30 minutes, we know they've done 30 donuts, right? That's just the rate, okay? And so the thing with the integrated rate law, it's not always a linear, like that donut example. Sometimes it's exponential. So let's do some examples of this and see. So the first example we'll do from your handout is thionyl chloride, SO2Cl2. So the decomposition of SOCl2 is first order. That's important. That is important. So what I would do, all right, for this, all right, just so that we have everything, because we want to make sure we have everything, okay, is I would write out that there's the natural log concentration of A in this case is SO2Cl2. Right? And we got time T times 0 and KT here. Alright? And T1/2 is equal to natural log 2 right over K. So we know, since it's first order, let's write down those equations. Alright. So that we got first order, and now we know that it gives you the rate constant is right there at a certain temperature. A asks, what's the half-life? What is so A is right there. What's the half-life? Well, for A, that's pretty straightforward. T1/2 is equal to natural log of 2 divided by K, which happens to be 1.42 times 10 to negative 4 seconds negative 1. So that means T1/2 would be equal to, looks like I have 3 sig figs, so 4,880 seconds. And there's the answer to number A. Pretty straightforward, I hope. Now B's kind of fun. How long will it take for the concentration of SO2Cl2 to decrease to 25% of its initial concentration? Well, if we go from 100% to 50%, that would be T1/2. And if we go from 50% to 25%, that's also a half-life. All right? So we have 2 half-lives here. Now, since it's first order, all right, we can just double the half-life. So for B, the answer should be, right, 4,880 times 2, which would be 9,760 seconds. But let's say we didn't do that. Let's say we didn't pick up on, oh no, what do I do? All right. Okay. So we would use this equation right here, the natural log, right, of thionyl chloride at time t over thionyl chloride 0 equals negative kT. And we're looking for t. So at time 0, time t, at time 0, how much percent do we have? Well, we have 100%, don't we? And we have 25% left at time t. K would be 1.42 times 10 to negative 4 seconds negative 1, and then we're solving for t. So how do I solve this in my calculator? That's a great question. So I'm going to pull up the calculator here, and we're going to solve it. All right. So you can, again, this is not, this will still work even if we do not realize that it was 2 half-lives. So I'm going to take the natural log, that button, right, of 25 divided 100, close my parentheses, and then I had to divide by K. Divide negative 1.42 times 10 to the negative 4th. 9762. So I get T to be 9762 seconds. And I only have 3 sig figs. So that's 9760 seconds, which is the same. So you get the same answer. Not that much longer, but longer. All right, now C is the same question. But C, we can't just use half-lives. Right, so if I look at C here, right, it says the initial concentration is 1 molar. How long will it take the concentration to decrease to 0.78? Now, since we're not at whole half-lives, we can't do anything like that. We actually have to use the natural log of the concentrations. So again, at time t, we're at 0.78 molar. At time 0, we're at 1 molar. So that's T0. And we got negative 1.42 times 10 to negative 4 seconds negative 1, and T. So again, we can just solve this the exact same way. In fact, what I would do is I'd hit second enter. Oh, doesn't my calculator, my TI-83, if I hit up, it goes to the front. So this was, the concentration was 0.78. So 0.7, I have to use second insert 8 divided by 1. I'm just going to put 0.0. That works. It's 1.00. Right? Enter. I get 1750. 1750. 1750 seconds, which is smaller than a Half-Life, which is good, right? Because it's less than that. Okay, so now I technically have only 2 sig figs, don't we? Because this limits me to 2. So really, it's 1800 seconds. All right, last but not least, D. So if we look at D here, it says initial concentration is 0.15. What's the concentration after 200 seconds? So I would use, for D, I would use the E form. Sounds like an electronic form, but it's actually not, right? I would do where you have thionyl chloride at time t equals the original concentration, e to the negative kT. So we have SO2Cl2. Now, of course, if you're doing this, you do not have to use color at home, right? I'm using color for you guys. And now we're actually looking for that guy, right? I don't know what's going on with my pen today. Sorry about that. Alright, so we're looking for the concentration of SO2Cl2 at time t. And that's going to equal the original concentration of 0.15. Well, didn't change. 0.150 molar. E to the negative K, 1.42 times 10 to the negative 4 seconds negative 1, and T is 200 seconds. Alright, so in my calculator, 0.15. You can put the 0 there, that doesn't do anything for you, but you can. Times, now I hit the second ln, and that's E. Alright, I'm going to put a parentheses, negative 1.41. It doesn't matter where you put the negative. Second E, negative 4 times 200. And we get 0.146. I have 3 sig figs, so 0.146. So that's at 200 seconds. Now at 500 seconds, the only thing that changes is in green, right? The only thing that changes would be in green, the time. Right, because that's what... Not moving. There we go. 500 seconds, right? So at 500 seconds, the only thing that's changing is up here, right there, the 5. So I can go back to here, really straightforward. Second enter, right? Move over to a 5, and boom, 0.140. And that's it. So that would be an example of first order. All right, the next example is of XY, and it's second order. All right, it's second order. So right away, I would write down, because we got second order, 1 over the concentration of XY at time t equals KT plus 1 over the original concentration of XY. That's 0. All right, I like to write this out just so we know what formula to use. And then we actually have a T1/2 formula here too, don't we? T1/2 is going to be equal to 1 over K times the concentration of XY. All right. So what's the half-life? There you go. So now we know we're using half-life for this reaction and an initial concentration of 0.1 molar. Well, that's a good question. So do we have K? I think we do. I think we have K. So there's K. So T1 half for A, T1 half would be equal to 1 divided by K, which is 7.02 times 10 to the negative third, molarity, negative 1, seconds, negative 1. That means they're on the bottom. And we're going to multiply that by 0.1, 0.100 molar. Now, we just got to make sure we do this math first, right? There we go. And so how do I do that? In my calculator, I would just hit 1, divide. Now, K, 7.02 times 10 to the negative third. Then I just hit the divide key again, 0.1. Right? I can do that. That way you don't have to use parentheses. You can use parentheses, right? I can do it 1 divided by 7.02 times 10 negative third times 0.1. And you get the same answer, right? It's just, to me, it's less keystrokes and less likely for me to have a syntax error. That's up to you. Okay, so it's 1420 seconds. Now, B is the same question we had in the last one. We're at 12.5%. So that's actually what? 3 half-lives. But I'm going to say danger. Right? Because each half-life is different in second order and zero order, right? They either get longer or shorter. Okay? And so they either get, each half-life is either twice as long or twice as short, depending on what order we're in. I don't want to make you guys, now if you can do the mental math and you're great at this and you're like, oh yeah, it's just this, go for it. Some of you guys are amazing at math, and please don't let me hold you back. But for those of us who are, that's not like an appealing idea, let's just write it out. Sometimes that's a little easier. So B, right? We'll use the 1 over xy at time t equals kt times or plus 1 over x0. xy 0 times 0. So the original concentration, or the concentration at time t, is, well, we'd have to multiply out, right? So if I know my original concentration, let's get this all together. K is 7.02 times 10 to the negative third, molarity times second. And then we have T, is what we're solving for here, plus 1 over the original concentration. So T0. The original concentration is, we're going to do 0.1, 0.100 molar. So now I need to do 12.5%. How do I figure that out? Well, when I just multiply by like 12.5%, this is 0.125, right? And that makes sense, right? So we multiply 0.125 times 0.1, and I get 0.0125, right? That's 12.5% of 0.1. And now we solve. So how do we solve? Well, I would have 1 divided by minus 1 divided by, all right, 1 divided by 0.0125. You can do the math if you want first. And 0.100 molar, because we had time t and time 0. I have to do that. Then we're going to do all this and divide it by K. 7.02 times 10 to the negative third, molarity, negative 1, seconds, negative 1, and that'll equal T. Won't it? All right. So if we do that, how do I do this in my calculator? All right, so we take K, 7.02 times 10 to the negative third times 50 plus 1 over 0.05. I should get 20.351. All right, 20.351. And if we do that, where we go here, so that means I get 1 over the concentration of xy times t is 20.351. I'm just going to round at the end. What's my units? Well, seconds are gone. Molarity is on the bottom, and we're adding them, so it's times molarity to negative 1. Well, now I multiply both sides by xy and concentration xy times t and divide by 20.351, or we can just invert them. All right, so you can write down xy at time t is 1 over 20.351 molarity negative 1. Right, in the calculator, all I have to do is just hit this button right here, that 20.35 to the negative 1, and I get 0.049. 0491 it looks like. How many sig figs do I got? I have 2, so 0.049. 0.049 molar, because that comes up top. Alright, and after 550 seconds, you would have to go back to the calculator. You can hit second enter, and then second enter. And I have to go over here, hit second insert 5, boom, and then 0.042. And so that's number 54. So hopefully that helps make some sense. All right, and there's one more I want to do for this video, and that would be half-life of the radioactive decay of carbon-14 is 5,730 years and independent of the initial concentration. That's a key, right? This right here is independent of the initial concentration. This tells you that all, well, it doesn't tell you all, but in this case this one, but all nuclear decay is first order. All the nuclear decay is first order. All right. And so, first order kinetics, then, I would have this, the natural log of 14c at time t all over 14c at time 0 is negative kt, and t 1/2, natural log of 2 over k. Right? How long? There's your question. How long does it take for 25% of the carbon-14 atoms to decay? Well, that would be 2 half-lives, doesn't it? So that's kind of question 1. Here's question 2. It's right there. Okay, so question 1, that's 2 half-lives, right? Because we go from 100 to 50, and then 50 to 25. So that's 1, 2 half-lives. So you would double the you would double the half-life, right? So that would be what? So that means the time would be 11,460 years. So that would be question 1, right? 2 half-lives. Now, for question number 2, for part 2 here, I need to find I need to do a couple things, right? Because we're looking for how many millimoles are left after 225 years. So I'm going to have 14C at time t equals 14C at time 0 e to the negative kt. Right? We have t. We got to get k. Luckily, t1/2 is equal to the natural log of 2 over k, or k is equal to the natural log of 2 over t1/2. So that's the natural log of 2 over 5730 years. So if I take the natural log of 2 and divide it by 5,730 years, I get 1.21. I use orange again. K would be 1.21 times 10 to the negative 4 year to the negative 1. So that's what I get for K. So now we can solve this problem. So I'm looking for carbon 14 concentration or amount at time t. I know the original, which happens to be 1.5 millimoles. E to the negative k, 1.21 times 10 to the negative 4 year negative 1, and t, which happens to be 2255 years, 2,255 years. And so my units of t are good. So what is 14C at time t equal to? So I take my 1.5 times e to the negative, what do we have here? 1.21 times 10 to the negative 4th times 2255. And I get 1.14 millimoles. Alright, so there's the questions, first 3 questions that we'll do. Alright, so hopefully that makes sense. With the first order, second order, hopefully it's pretty, and you got a nuclear one in there. And we'll do some more examples in the next video. Take care, guys.